Hello and welcome to GOTO Book Club. My name is Tim Misiak and I'm an engineer at Datadog, formerly working on debuggers at Microsoft. Today I'm thrilled to be talking to Cy Brand, author of the excellent book, Building a Debugger. Cy, in addition to being an author, you're also involved in C++ standards and tool chains through your work at Microsoft, right?
Yeah, so my name is Cy. I work as a Microsoft C++ developer advocate, so I wear a lot of hats. Sometimes do C++ standards work, do conferences, done work on this Microsoft C++ standard library, and my background is in debuggers and compilers for GPUs.
Okay. So, even as I just opened this book, I knew I was going to love it. I have a background in debuggers, but, I open and I see the title page and it says, building a debugger, deepen your operating systems and system programming knowledge. And I think that really describes my experience with learning about debuggers just really well. There was so many things that I learned through, working on debuggers that, I learned way better just by implementing a debugger than I could have through pretty much anything else I can think of. So this book, it's not just for people that want to build a debugger, though, right? What other types of people are going to, benefit from reading this book and find it interesting?
Yeah, I mean, I think that in building a debugger, you learn so much about how computers actually work, which you can apply in pretty much any kind of area of development that you're doing. If you're doing systems programming, then understanding what's actually going on under the hood can be invaluable. So it can help you understand hardware, your operating system, how it interacts with like the interface between those things, the kinds of things that your operating system is providing to your programs, how to make the most of your debugger or find out why there are issues with your debugging workflows, because now you understand how these things actually work. And you say, oh, well, if I'm not getting the value of this variable in my debugger, or stepping's not working, it's probably because of this thing or that thing. And like you understand how these things actually work now.
Yeah. Understanding how the hardware works and understanding how the operating system works. It helps when implementing low-level software, I think. But like you said, I think it also helps you more effectively use a debugger. I didn't know about memory access breakpoints before I started working on debuggers.
Yeah, actually,
hardware works and stuff.
Which are super useful. And yeah, I had never really used until I implemented them, and it's like, wow, these things are so cool. I should use these more.
Yeah, that would be something when people would join, our team at Microsoft to work on debuggers. I would also be teaching them debugging features as well, and they say, "Oh, you can break into the debugger when this memory changes." That's a game changer. That's really cool.
Yeah, for people who aren't familiar with this is you can set, as well as breakpoints, which you can set on a line of your code to say, hey, stop when it reaches here. You can also set them on like reading from or writing to a memory location. So if you have like some memories being corrupted, and you want to know, hey, what is causing this corrupting write? Then you can set a memory breakpoint, and every time it's updated, you'll stop your program and you can find out what's going on. So handy.
Yeah, absolutely. So you already kind of mentioned that you sort of learned about, how hardware breakpoints work as you were implementing debuggers. Anything else that sticks out to you as sort of like things that you learned as you started, working with debuggers?
Stack unwinding is a big one. But before I wrote this book, I wrote a series of blog posts on writing a kind of simple Linux debugger. I know you did a similar kind of thing in Rust for Windows. But I never really touched stack unwinding much. I was kind of like, oh, we'll write a basic stack unwinder that just assumes that you're compiling with frame pointers, which is sometimes true and sometimes not true. And they simplify stack unwinding a lot because they basically allow you to just walk up the stack by reading a known memory location from your current function's stack pointer, and then you're golden. But if you don't have that, then you need to read like the stack unwinding tables, and they're horrific. I never realized like how much nonsense is built into stack unwinding. There's like an entire Turing complete language built into the stack unwind information on Linux, and it's horrifying but fascinating.
Yes, horrifying but fascinating. I think describes a lot of that. I found the same thing with stack unwinding. I'm more familiar with the Windows side, but it's just as terrific. There's so many crazy edge cases, and the version that maybe you learned in school, if you had a operating systems classes, you learned the frame pointers, and they make it look so easy, and they say we're going to walk the frame pointers now, and you just sort of dereference some memory and walk along, and then the real world hits, and you have things like the inline frames, and you have interrupt handlers, maybe if you're dealing with hardware, and maybe you have a bunch of different little edge cases on different types of CPUs and stuff. And of course, the Turing complete unwinding language that you get in the frame descriptions. And that was, I loved reading that chapter in your book as well around stack unwinding, because, I have the Windows perspective, and I thought, oh, maybe it's better in Linux. Maybe they have something unique and interesting now. It's hard. There's a lot of optimizations and things that you have to deal with.
Yeah, I also found that I expected to be able to, because I didn't understand all of the things that went into stack unwinding. I assumed, this must be documented in the DWARF standard or the System 5 API or something. So I'm just going to read one of these documents, and this is going to tell me how to unwind the stack, right? But no, there's 3 or 4 different documents that you need to read, and they're all slightly inconsistent and sometimes even contradict one another. And then you go and read the source code for GCC, and that contradicts the specifications and also has some other extensions that you have to implement because everyone follows what GCC does on Linux because it's like the de facto standard. So it's horrible. It's awful, but again, fascinating.
Yeah, and that tends to be the case, I think, with a lot of things that reach a certain complexity. Like the real documentation is the source code, and sometimes even that's not going to agree because maybe GDB is going to do something from GCC, which is going to do something different from Rust.
Or even do different things on different platforms, which GCC absolutely does for stack unwinding. Like if you are on x64, then certain types of stack unwinding information mean a different thing than if you are on ARM, for example. It's a mess.
Yeah. So you seem to be a little familiar with both the Windows side and the Linux side of debugging. Sounds like you started with the Linux side first, right? Yeah,
so I'm definitely a lot more familiar with the Linux side. Like my entry into debugging was because I got a job nominally as a compiler developer, but then my first task was to get debug information outputted by the compiler and then make sure that ended up going through all of the data pipelines for LLDB, which we're using for the debugger. And that's all kind of Linux-based stuff. So all of my kind of hands-on experience with debuggers was with Linux, and then I just looked into Windows stuff through interest because I wanted to know what was going on. So I have a kind of perfunctory understanding of debugging stuff on Windows, and then have witnessed all the horrors in Linux.
Do you find, with what you've seen from Windows, does it seem like the main concepts are mostly the same between Windows and Linux, or is there anything that sort of stands out to you as sort of different or surprising?
Yeah, I think that a lot of the major concepts translate over pretty directly. Some things take different approaches, like the main system call interface for Linux is like a single function, which is horrible API design, but it kind of works, whereas Windows has more ergonomic, let's say, system call interface for doing the low-level debug features. So it's always interesting to note the kind of differences in approaches, and these things all come from a lot of history and of kind of accrued more and more features and complexity as the years have gone by, but then they develop in slightly different ways. So it's always interesting to note those.
Yeah. Something that I found really interesting reading through your book was just sort of seeing how Linux and Windows have very different philosophies when it comes to things like threading, and that reflects itself in debugging APIs. I was surprised you could even talk about things like register context and such without really even touching on threads, because you can just have a process that has a register context. And that was kind of different for me, because all my background is Windows, and Windows is like, oh, nope, threads are just sort of a assumed concept. You've got to, when you get a register context, it's for a thread, not a process, it's for a thread. And I thought that was really interesting, that, sometimes sometimes the APIs and interface that you talk to the OS reflect some underlying philosophies about how the OS is designed as well.
Yeah, absolutely. Like in Linux, the delineation between a process and a thread is very, very thin. Like they're both implemented as tasks in the kernel, and most of the differences is in how they inherit things like memory mappings and file handles and all of that kind of stuff. They're dealt very similarly in the scheduler and the ptrace interface and all that. So you can kind of, at the start at least, forget that threads ever exist, and you just have a process and you deal with that. And then you're like, okay, well, threads exist, and maybe we should handle these.
So you kind of alluded to, like, these are very old interfaces. They've evolved over a long period of time. And I think, you can see in both the Windows and the Linux side that, these are sort of some of the earliest things, and they don't change often. Sometimes, the debug formats or the executable formats, sometimes they don't change because there's just no strong incentive to break compatibility. And so you get some of this long history, and sometimes you see in the formats, it's a little bit of an archaeology. You can see, like, oh, there's this field, it's not used anymore, but here's what it was used for. If you had the opportunity to go and sort of like design things from scratch, right? Is there anything that stands out to you, something that's like just really gnarly that would be nice to sort of like start from a clean slate?
Yeah, I think there's two main ones. The first is ptrace. Like I mentioned, that ptrace is like a single function call that you use to implement like low-level debugger features. So that's things like reading a word of memory, or writing to memory, or stepping over a single instruction in the processor, or doing maybe like 20, 30 different things in this single function. And depending on the kind of request you're making, whether it's writing to memory or stepping or any of the other things that you can do, it treats its arguments differently. It might even report errors differently. Like some of the requests you pass to ptrace, you have to check the status that it returns. Some of them you can't do that. You have to like reset errno before you call it, and then check errno after you call the function to see if it succeeded. And it's kind of a nightmare. And they add more and more requests over time to support some newer kernel features and things like that, and it all becomes a bit of a mess. So yeah, I would definitely like a modern interface to doing those kinds of low-level debugger tasks. The other one is DWARF information, which is the debug information format for Linux, which has 3 different custom bytecode interpreters that you have to write in order to parse it, which is it's kind of a nightmare. I mean, so the reason that exists is because DWARF was designed to have the lowest memory footprint that they could really achieve. Like a lot of DWARF is just really, really large tables. Like line information maps some memory address, a virtual memory address of an instruction of your code back to of the machine code generated by your compiler, maps it back to a line of your source code. So the line table becomes ginormous if you've got like 1 million lines of code in your project or whatever. And DWARF goes to very, very large extremes to try and minimize the amount of memory that you actually have to hold for that. So you don't store that large table, you store a program which generates that table, and then your DWARF interpreter has to interpret that program. And DWARF's full of that kind of stuff in a way that's not as relevant today. It's still nice that we don't have to store very, very large tables, and we have ways to slowly build them up in memory. But it makes writing a DWARF consumer very, very difficult, especially when you have to deal with multiple versions of DWARF because they're not backwards compatible. Like if you write a DWARF 5 parser, you can parse exactly DWARF 5. You can't. They will introduce new fields into the information. They'll change generally not how existing instructions work, but they'll add more things to them that makes them incompatible with older versions. So if you're writing a DWARF parser that wants to work with anything from DWARF version 2, which is kind of the lowest one that anyone uses anymore, up to DWARF 5, which is the most recent standard, you have to do a ton of work. I mean, it's enough work to write a DWARF 5 parser, let alone a DWARF 2 to 5 parser. So yes, ptrace and make DWARF reasonable.
Make DWARF reasonable. Yeah, the backwards compatibility problem is always hard. So many times, and I guess it's almost it's same Linux versus Windows here. We would, when we had a Windows debugger, and we'd say like, yeah, we'd like to drop support for this old, debugging format that was generated by, Visual C compiler version 2 or something. And somebody would come to us and say, actually, there's a line of business app that, some company needs. Could you please just leave that in there? It's not hurting anything. And then you get all these different versions. And they're all mutually incompatible. I totally understand the desire there with DWARF to let's make this as compact as possible. And back then, I'm sure when the standards, I don't know when they came from, but I'm sure it was space was at a premium. And now, maybe space is not quite as a premium, but we have much larger binaries. We have things like the Chromium, builds that have symbol files that are over 4 gigabytes in size. And you say, okay, well, maybe there's other ways we need to think about compressing these that we, as well as still have fast access. So it's not you're doing linear searches through 4 gigs for to find your local variables and things like that. I do wonder what we'd come up with. We could design something from scratch. I always sort of dreamed about that, but reality is a lot of times it's good enough, and maybe you can tweak it a little bit, and I think that just sort of accumulates over time.
Yeah, especially because there's as languages add more and more high-level features that you need to kind of percolate through the debug information so that when your debugger eventually gets some, block of machine instructions, they can map that back to, use the C++20 feature, and we want to be able to visualize that properly in the debugger. So now, okay, we need to add something to the DWARF information in order to be able to express the C++20 concept, and redoing all of that from scratch is a huge undertaking.
Yeah. And language features always have that push and pull with complexity with debugging. Of course, the example some people are familiar with is, and you talk about in your book, is sort of the mangled names, where you have sort of these name overloading and characters that can show up there that would not be in sort of a C style name. But then you get into things like anonymous functions, and you get into captured variables and closures and things, and then you have languages like Rust that come out which come up with new concepts, and trying to map that to existing symbol formats versus coming up with new things. So it's very hard. That would always be something that we would have to think about is, there's a new language feature. How do we even make sure that this is debuggable?
Yeah.
And that's not even touching things that I think are really, really difficult, like some of the things like async and C# and other, newer, languages that have been designed in ways that don't fit into the same sort of debugging concepts that we've been working with from, starting from the C days, right?
Yeah, and that's the kind of stuff that, to come into like job-related stuff, like on the Visual Studio debugger, like making C++ 20 coroutines debuggable. Like as this is kind of the C++ version of async await or whatever, where, okay, if you like suspend some coroutine, how does that work? Do you like go back to your caller? Do you just end up at the next part of the coroutine? Do you end up in some like runtime function that you have no idea what this is, and it's something the standard library implementers wrote and you don't care about? These are all problems that need to be solved in sometimes creative ways by tooling vendors, and which touch on like the debuggers themselves and the debug information and the linker, and just everything needs to be touched in order to get all of this information through the entire toolchain pipeline.
Yeah, absolutely. I want to change gears just slightly. As I was reading through chapter 14, which talks about stepping through code, that's something, earlier we talked about sort of stack unwinding and stack walking is something that's very complicated. And I think in some ways you figure out pretty quickly that stack walking is complicated, thinking about, especially as soon as you realize that it's not just following frame pointers. I find stepping through code to be something that is more unexpectedly complex. And the deeper you get into it, the more complex it gets, not the simpler. It never really sort of gets easy. I guess on as far as like stepping is concerned, do you think there's aspects of language design and compilation that has an impact on sort of like how can we actually support stepping through code?
Yeah, I think you're right that it feels like it should be a lot simpler. So when you look at stack unwinding and you're like, oh, we need to somehow encode like where all of the variables are located at different program counter values, and we need to define how to like restore registers and stuff. That sounds complicated. Stepping, you're just like, oh, go to the next line of code. Like that's simple, right? But then you're like, okay, so what does the next line of code mean? And suddenly it becomes very difficult because maybe you just want to like you think about it and you're like, okay, well, I'll just keep stepping through instructions of my my machine code until the line information for my current program counter changes. Like that. That's one way to think about the next line of code. But then what if you're implementing like stepping into functions versus stepping over? What happens if you hit a branch and you end up in some other function? What happens if you step into an inline function, which is an absolute nightmare to deal with, because suddenly you're like, oh, well, for inline functions, for people who don't understand how those get compiled, they would just basically take the machine code for that function and just dump it into the context in where you call the function. So it's like a copy paste job rather than a function call. So you're still like logically within the same function you were originally in the caller, but now you're also kind of inside the callee. And how do you visualize that to the user? How do you decide what to report if I'm at the top of an inline function and I step in, because there's no actual change in the program counter in that case, and you have to deal with all of these edge cases. And then you start thinking about, okay, well, what if I'm trying to step to the next line of code, but I jump over a function execution and there's a breakpoint set there. What do I do then? And then you're like, okay, well, do I just disable that breakpoint? Do I hit it and report that to the user? How do I keep the code for my stepper vaguely understandable? It becomes a real problem. And yeah, to go come to your question of like how high level languages interact with that, I think that it complicates matters when suddenly you're like, you're in an if statement where the condition is broken over multiple lines, and the ways in which that is encoded in the line table information and how you're going to deal with it in your debugger. These are all things which just make what seems like a very simple question very complicated.
Yeah, for sure. You're talking about sort of like thinking about how to design that stepper so that the complexity doesn't sort of blow up. Do you have thoughts on like if you were implementing something that's meant to be a production debugger, how would you approach it? Like high level, like what does that stepper look like so you don't explode your complexity?
Yeah, that's something that I put a lot of thought into when writing the book, and I ended up going for something overly simplified for the book implementation, where basically I implement functions which do implement step over and stepping out of a function and stepping into a function, and those kind of deal with themselves the problem of, oh, what if I hit a breakpoint or something like that. I quite like how LLDB, LLVM's debugger deals with this. They have the concept of thread plans where you have kind of a stack of thread plans which say, okay, well, I'm currently trying to step over this range of program counter values. And the reason I'm doing that is because the user asked me to perform this kind of step operation. But also I might hit a breakpoint at some point and I want to be able to report that to the user. And they kind of build up this stack. And when there's a program stop, then it will ask all of those different thread plans, hey, like, do you understand why this happened? And do you have something I can report to the user? And say, okay, well, no, this is irrelevant to the reason that I was stepping. So you ask the next one, and that said, oh, yeah, this is my one. This is my stop. And then you report that back to the user. So that works quite nicely in keeping the code itself not so much understandable, because there's a lot of machinery that you kind of have to work through if you're trying to comprehend how all of the stepping code works, but it keeps it maintains a separation of concerns, right? You're not thinking about, okay, well, I'm currently stepping, so I need to think about any breakpoints that can be hit during this and dealing with all of those in my code. It helps you think, okay, right, I'm writing something which is saying this is my thread plan, this is what I'm trying to achieve, and then you write other thread plans which try and achieve other things, and you kind of compose those. I do quite like that design.
Yeah, it's almost like you've got this meta language that's describing sort of the interactions, or you guess you could think of it as a state machine that's sort of describing the interactions between sort of like what we're expecting, what might be happening in the other process, and try to model that back. That almost seems like a common, like, besides sort of the meta languages that are built into the symbol formats, the bytecodes, it seems like these sort of meta languages, pop up in a number of places in debugging. You can think about things like expression evaluation or type visualization. If there's some great technologies that are things like NatVis, which lets you visualize some of these physical types into something that's a little bit more logical, but they all sort of end up being sort of these meta languages that describe interactions between symbols and debugging targets and users. And it just sort of seems like built into, what we're doing, because we're dealing with languages, we're dealing with, state machines and I guess a little bit of compression on the side there with DWARF.
Yeah.
Was there anything with stepping that maybe while writing this book, was there anything with stepping that you learned that maybe wasn't obvious with some of these interactions? I guess we've talked about stepping a lot, but does anything else come to mind?
Yeah, I think I had already delved into some of the icky parts of stepping when I did my original blog post series many years back. So I already had a reasonably decent understanding of how it worked, so there wasn't any major surprises. But it was something where as I was writing the early parts of the debugger and the early parts of the book, I was like, oh no, I need to get to stepping eventually, and that's going to be a nightmare. There were a few chapters like that. Yeah, stepping, stack unwinding. Well, actually, the stack unwinding was more of a surprise. I was like, oh, that'll be fine. It was not fine. And then expression evaluation, as you mentioned, that was the other one. That was like, how on earth am I going to write a chapter on expression evaluation that doesn't start with, okay, go write a compiler?
Go write a compiler. That's right. Yeah. Yeah. I think there's a distinct way you have to approach things sometimes when you're trying to teach it, because there's a lot of, sometimes there's a chain of prerequisites that you say, okay, I can explain this, and then I can explain this, and then I can explain this. But sometimes there's this web where you're like, well, to explain stepping, we're gonna have to assume, a little bit of assembly language, and there's gonna be a little bit of like, well, we've got this disassembler and things like that. I think it can be hard to teach because all these concepts are interrelated sometimes.
Yeah, trying to map out all those dependencies was something I did quite early on when writing the book. So I knew pretty early on that I was going to have an entire chapter right at the start dedicated to, like, okay, here's the things you need to know about, like, compilation, about computer hardware, about operating systems. This is like prerequisite knowledge that you will need for pretty much the entire book. So I wrote all of that down, and then I was trying to think, okay, so in order to implement like certain types of stepping, we're going to need breakpoints. So we need to have breakpoints first. In order to have breakpoints, we need to, and you kind of map all of that stuff out. I think I did a mostly good job of that. I did have to shuffle things around a few times and, move chapters as I realized, oh no, suddenly I'm reaching for this thing that I haven't explained yet, and explaining it would be like 20 pages, and I don't want to just embed a 20-page aside in the middle of this chapter that's about something completely different.
Yeah. Sometimes you have those 4 references, but I thought the way that you structured the book, as you mentioned, I've written some blog posts about it, but I came from it from the perspective I'm writing a debugger for fun. I'll write some blog posts about it too. And then you try to think about like how to teach it. But I think you've done a great job of like structuring some of the prerequisites that everything sort of like logically flows, even though there's so many different interrelated things. I think it's very understandable if you, maybe I'm not the best person to say coming from no debugger background, but I'm certainly not a C++ expert. And I loved how the book writes it in a way that sort of, is very much like, let's use the language to be as effective as possible. And I didn't feel lost by any of the C++ or anything.
Thanks.
Just a great structure with how it teaches. If I was still on the debugger team, I'd say it was required reading. Even though it's limited, it's required reading. So, looking forward towards the future, I'm sure you have thoughts on sort of like where debuggers are going. And I know a lot of that is maybe closely related to, language evolution and operating system evolution and things like that. But is there anything sort of within the just debugging realm as itself that you're sort of excited about or looking forward to, maybe in hardware or AI things that you think are going to be interesting with debuggers?
Yeah, I think a couple areas that are very interesting to me is time travel debugging, which has developed a lot over the past, we say, like 5 or 6 years, maybe. It kind of ballooned, I'd say. Maybe a little bit earlier than that. I'm trying to remember when things like RR and UndoDB and things like that started to really kick up. But I think it's a really interesting area because, so often especially if you're debugging like multi-threaded programs or anything with like non-deterministic parts, you're like, oh, I finally got the program behavior that I needed in order to that actually shows a bug, and now I need to go back and debug it. But oh no, the thing already happened, and now I can't go back anymore. And time travel debugging helps you go back and be like, okay, so why did this thing happen? So yeah, I think very interesting to see where that goes and if there's more developments in that area. Another one is debugging optimized code, which I think there's still a lot of space for improvements. I didn't really address debugging optimized code a lot in my book because it's usually when you're writing when trying to understand debugging, it's good to assume that you have things like debug information and symbols, and that your program is not jumping around all over the place. Trying to assume a more ideal picture of the world. But when debugging optimized code and writing a debugger for optimized code, things get very, very gnarly. And then when you're actually a user of a debugger and you've got optimized code that you're trying to debug, the experience is usually not good because your variables are optimized out. You're not able to, you step somewhere and it goes somewhere completely different. There's more inlining, which becomes a nightmare to handle. So I do think there's a big tooling opportunity in the area of optimized debugging.
Yeah, the time travel one in particularly, I've worked on time travel debuggers before, and I always found that it's when people start to see what's possible, a lot of people just don't even know that these things exist.
Right.
They've never tried RR, they've never tried WinDebug time travel debugging, or they've what is it, UndoDB, I think, is one of the other ones, and it's really kind of amazing when you start using these things. And I think there's a lot more that could be done there too. People say, it's hard to reproduce my bug. Well, you just have to reproduce it once if you can record that repro, and now you've got a definitive root cause. And certainly makes some bugs shallow when you can see, oh, hey, I've the stack has been overwritten. Well, who overwrote my stack? Well, just reverse execute and go back to it.
And use memory breakpoints.
Exactly, use memory breakpoints. Yeah. That's one of those things that I think more people should just be aware of, it's a tool that they should have in their tool belt.
Yeah.
And of course, the optimized code, there's always that push and pull around. Let's make compilers more efficient and eliminate more instructions, but also somehow still make it understandable when you're stepping through it.
Yeah.
Those are hard problems to solve.
Yeah. So many trade-offs.
Yeah, for sure. Well, it's been absolutely great talking with you, Sai.
Yeah, you too.
A wonderful book that you've written, and highly recommended anybody that's interested in debuggers, but also anyone who does systems programming or anything like that. Just a fantastic book, really in depth, really approachable, and a great book for anybody that's interested in the topic. So
thanks very much.
Thanks very much, Sai. It's been great talking to you.
Yeah, you too.
Subscribe to the GOTO YouTube channel now and join the experts in person or online at any upcoming GOTO conference using the promo code Book Club. Visit gotopia.tech to learn more.